All right, so good evening, everyone, or good morning or good afternoon, wherever you may be. Thank you very much for coming to our webinar this evening on hallucination-free zone, large language models plus graph databases, got your back. So this is an ACM Chicago webinar, and I am the chair for ACM Chicago. My name is Alvin Chin. Maybe most of you have already attended our previous webinars, so thank you for attending this one. And we're also co-hosting. We actually have some co-hosts for our webinar tonight. So we also have IEEE Computer Society, Chicago chapter. Some people tonight are from that. And also as well, IEEE Chicago section. And also as well, we actually have some members from the IEEE New Jersey section too as well. So we have a wide range of a crowd this evening. So thank you very much for your time this evening, sacrificing your dinner time if it's dinner for you guys. But thank you very much, really much appreciated. All right, so most of you have already heard about this meetup from our meetup website, ACM-Chicago. And we also have as well for IEEE Chicago Computer Society too as well. So just a bit of introduction. So I'm the chair for both actually ACM Chicago and IEEE Chicago, and also IEEE Computer Society Chicago. We have Mark Temkin, who is our vice chair for ACM Chicago. We have Greg Newmark, you see here on the second on the slide. He is our treasurer. And then on the right is Gina Martinez, who is our vice chair for IEEE Computer Society Chicago. Before we introduce our speaker this evening, Jennifer Reif, just a bit of housekeeping rules. This webinar is being recorded. You will receive a copy of this recording once we have finished editing the video. So you will see that in our YouTube video channel, which we will show you the link to that at the end of this webinar. Also too as well, you will also get a copy of the slides. So we will provide that too as well. If you require a professional development hour, PDH certificate, continuing education, you can email me, chair@chicagoacm.org. And we can provide you a PDH certificate for that. And then as well, if you have any questions for Jennifer, we will go ahead and address them at the end of her talk. So please put them in the Q&A that you see in your Zoom. And then we will go through it. Please don't put into the chat, put into the Q&A, and then it's easy for us to go through each one of them and address it. Okay, so I think that's pretty much about it from me. So I'm going to turn it over to Vice Chair Mark Temkin to introduce our speaker this evening. Go ahead, Mark.
Okay. Hi, everyone. Thanks for coming. Great turnout. And I'm sure we're all looking forward to hearing Jennifer Reif from Neo4j. So let's have a big internet round of applause for Jennifer Reif and Hallucination-Free Zone.
So we're going to talk about hallucination-free zone, LLMs, and graph databases. Got your back. So my name's Jennifer Reif. I have my contact information there in the lower left of the slide. It's also on the next slide and on the final slide too. So if you think of something, a question after the fact, after the event is over or weeks down the road, feel free to reach out to me. I'm more than happy to talk tech and answer questions about Neo4j and other types of stuff via any of those channels. So very quick background on me. I'm a developer advocate at Neo4j, have been for the last 6 years or so. And I like learning. I enjoy technology. I like learning about tech, and then I like sharing that technology in a variety of different ways. So whether that's through events like this one or conferences or tech blogging or videos or so on. I have a few hobbies outside of work. Most of them just boil down to the fact that I'm kind of a geek at heart, if you can't tell from the picture on the slide there. So, all right, we're going to dive right in. We have a lot of ground to cover here. Most of us are probably familiar with the database entries in the market, but I'm going to kind of give a quick highlight of kind of some comparison and contrasting, so we kind of know where graph databases and the latest vector databases kind of sit in this kind of grouping now. So first off was relational databases back in 1979. Oracle was the big name, kind of the big public name for this back in the day. And so the good things about relational databases is that you had these slices of data. So you had tables and rows and columns, and you could assemble those different slices in a variety of different ways using queries. You also had very low data duplication. You had a very easy way to create unique rows using some set or a single primary key, right? The downsides to this is you have to assemble all those relationships with joins, assuming you're using the normal form, first, second, third normal form as kind of the standard for creating a unique low data duplication row in a table. And so in order to assemble those unique rows into something potentially valuable or connected, you'd have to do that using SQL. So basically at query time. That can be kind of cumbersome when you're doing a lot of joins across a lot of tables and so on. You also have a very strict model that's going to be set up front. You organize that data model up front, and then you put the data into the database based on that model. And it is very strict. It's hard to refactor it. It's hard to change data types. It's hard if the data you're trying to import doesn't quite fit the data type it expects or the length it expects and so on. So there's some downsides, but it's been kind of a workhorse for many decades now. Next onto the scene really was document databases, and this was made popular by MongoDB in 2007. Again, there's a lot of other options out there too, but kind of MongoDB was the big name. So the pros on this is to kind of combat some of the things that the relational databases didn't handle very well. The document databases could handle a bit more unstructured data more easily. It's going to group the related info into a single entity, so you're not having to do as many joins potentially. But the downside to this is it's not as flexible because your relationships are going to be pre-baked into the document. So kind of adding on additional relationships is a little bit cumbersome. You're also going to end up with a little bit more data duplication because now you have these pre-baked sub-entities into different types of main entities. And so you have a little bit of data duplication, and then also refactoring that and keeping that up to date with good data integrity is a little bit tougher. Then we came to vector databases. And actually, Neo4j entered the market long before vector databases, but I want to kind of do graph last. So vector databases, and they're by no means is Pinecone kind of the first one, but it's kind of the one that hit mainstream, right? Everybody knows when they think of vector databases, we probably think of something like Pinecone, right, in 2019. The good thing with vector databases is it's very fast to retrieve highly dimensional data. And we'll talk a little bit more about that here shortly when we talk about vectors. And then running similarity searches based on the vectors, not on specific values. So previously with document databases and with relational databases, you were searching for particular values. Find data that has a location of Chicago or find this subset. You could even do fuzzy searches, but you were still somewhat looking for a very specific value. Look for something in this general region, or find something with this type of feature. But again, very specific values. The downsides to vector databases is it's going to need a lot of infrastructure and power to run these heavy computations, and you're not going to be able to store a lot of data outside of the vector itself and a little bit of metadata. Graph databases came onto the scene. Neo4j was the first entry to the market here, although there were some network type databases and things previously in previous decades, but Neo4j kind of was the first entry to the graph market in 2007. The good things here is it's going to combat some of the frustrations of relational databases as well, and kind of flip the restrictive data model on its head by creating this very flexible, agile data model. So it's very easy to refactor the graph and refactor data in a graph. And then also, it's going to store the relationships with the entities. It's going to make join operations very visual, and it's going to make join operations very quick to read because we're storing the relationships with the entities themselves inside the database. The downside to this is when you're storing the relationships in the database, it is going to create a little bit of write overhead. Because again, you're not doing those joins on query time, you're doing them on write time. And then for low connected data, for things that are very tabular, not a whole lot of joins, things like that, you're not going to get any benefit over a relational database there. Okay, so what is graph? What does it look like? Where is it based? Where did it come from? And actually, the foundations of it were created all the way back in the 1700s with a mathematician named Leonard Euler. It started with a math problem. There was this puzzle in a newspaper. You had 4 land masses and 7 bridges in the city of what was then Königsberg, Prussia. And so they wanted to solve the problem. If I start in one particular location, I cross each of the 7 bridges once. Can I come back to the starting point and not retrace my steps at all? This problem was not solvable, by the way, but the math that Leonard Euler used to try to solve it is what formed the foundation of graph theory, are built upon. So now we have something new with graphs. What problems does it solve? It's going to document the path of the data, not just the data itself. So how did we get here? It's going to answer how and why did we end up with this answer. It's going to help you understand, possibly find some hidden connections that you may not have realized were there before. Also helps you find alternates or the impacts of certain things, changes and logistics and so on. So graphs are going to help you add context and meaning to your data, which is going to help you build hopefully some better decision making. Some use cases that graph is used for, there are many, many more use cases out there, but these are kind of the highlight ones that people always think of. So recommendation engines, things like product recommendations or personalization recommendations. So the social graphs, where you're looking at who's connected to who in social media, supply chain for analyzing impacts or bottlenecks or raw material changes and so on of a supply network, fraud detection for finding and eliminating bad actors in a financial network, and most recently, generative artificial intelligence using graphs as a grounding agent or retrieval augmented generation or RAG to help combat some of the issues of hallucinations with LLMs. So again, lots more, but these are kind of the key ones. The too long don't read of graphs is you're going to get data storage with relationships. It's going to store the relationships with your entities. It's going to help you produce really fast read queries, especially when you have a lot of joins. You can connect different entities together as well as different data sources. So you could dump a whole variety of different data sources in and connect those together. And this is going to help mimic real world data organization, which is pretty valuable and powerful. Okay, let's build a graph. We're going to take, for example, a domain of books. I like to read. And so if we were trying to solve problems to look for authors with reviews for multiple books, or maybe we want to find similar users based on the reviews of books and their related authors and so on. These are kind of complex problems. You're dealing with a lot of connections and a lot of hops, potentially a lot of joins. So we're going to take this data model and the image there on the bottom half of the slide. We have our books entities in purple. We have authors that are connected to those books. We have reviews that were written for those books and users who published those reviews. Okay, so nothing overly complex, but we're going to see hopefully how powerful all these connected entities can be. So a property graph consists of node and relationships. If you're familiar with the mathematical graph theory terms, those are vertexes and edges. And so nodes represent objects or entities. You can label them, so kind of categorize or group them. In this instance, on the right, we have nodes that are labeled with book, author, and review. You can also have properties, which is metadata, usually key value pairs. So for instance, our book has a title of Star Wars and it has an ISBN, and your author, we have a name and an average rating for that author. And our review will have a rating and a review text that somebody can write their review, and then maybe some votes. Now, relationships, you have to have a type. So I kind of think of this as kind of a label for relationships. You also have to store it as a particular direction, in a particular direction. So in our example, we have an author who authored a book and a review was written for a book. So book kind of becomes our central entity because everything's kind of feeding to that. And you can have properties on relationships. So a review was written for a particular book on a specific date and time. So you can actually store that information on the relationship itself. Okay. Now let's kind of switch gears from graphs and we'll talk a little bit about vectors. Okay, so what is vector search? Well, first off, what is a vector? And there are kind of 3 components here. You have a length, you have a direction, and then those components together are going to have a meaning. So what's going to categorize things as being similar in vector world? So we're going to take an example of shapes here. Which shapes are the most similar? Well, by creating vectors, which is basically just a list of numbers that represent the object's characteristics or features, We can see here that the first vector on the top trajectory there, we have something that's not very long, but very, very wide, right? Kind of tall objects. And then the second trajectory there, we have something that's kind of much longer, but a little bit less wide, maybe. So you kind of have this different set of shapes and characteristics. And then the bottom vector there, you have something that's really, really long and not very wide at all. And so those things that are along those trajectories are going to be categorized as similar. So what does this allow us to do by categorizing something in a series of numbers? It's going to allow us to do something like vector arithmetic. So take the vector of the trajectory of A, we have a trajectory of B. We know A and B, can we determine C? Well, some of us who, have had a little bit of math at least say, well, yeah, that's kind of Pythagorean theorem, right? If I have C, or if I have A and B, I can figure out C. But let's kind of apply this to something different. This isn't just a mathematical concept. Now we're applying this to things like words, so text. So for an example here, we have a vector representation that kind of holds together all of the features and characteristics of the word king. So everything that kind of king means and what it entails. We also have that vector representation for man and for woman. So if we take the vector for king, we subtract the value of man, we add the value of woman, that'll give us something like a vector for queen, right? Because those characteristics for king and queen are very, very similar. The only difference is you subtract man, you add woman. And that is kind of you'll have those same general characteristics for queen. So this becomes really, really powerful when you start applying to words or even some other types of data formats. So what are vector embeddings? You're basically creating vectors for different data formats. So for things like audio or text or videos, you're taking all the features and the characteristics of that, you're converting it to a very long set of numbers, either hundreds or thousands of dimensions here. And a dimension is going to be just an interesting feature or characteristic. And you're going to basically convert it to a point in space, a trajectory, a vector. And then you can use that to do things like vector arithmetic or do similarity searches for what's close to this vector and so on. So, okay, why would I want to index? You always hear about maybe vector databases and creating these vector indexes. So why would I index? Why do I care about this? Well, as you might imagine, if we vectorized the entire English language, every word in the English language, that would be a lot of vectors that you'd have to store. So every time you would have this word and say, find the most similar vectors to this word, or, how do I understand this concept based on what's similar to it? As you might imagine, the queries could become really expensive. And that's just the English language. We're not even talking about, global languages here, because you need to compare every vector to the query that you're sending in. So indexes here are going to help you with speed, as they kind of generally do in regular databases. It's going to help you jump to right where you need, kind of like an index in a book. And then it could also let you pull however many closest vectors to the one you're searching for. So do an approximate nearest neighbor algorithm. So KANN. In this case, as an example, we could pull the 20 closest vectors or 50 or 5 or however many we want to determine. So let's take an example of vector indexing. So let's take a library. We're dealing with books tonight, right? Typically, libraries will categorize books by author, by genre. But let's say maybe you don't know the author, you don't know the genre, and those are kind of broad general classification systems, right? Embeddings can hold much more complex and specific information. So for instance, further categories, you could define the gender of the main character or the main location of the plot. Let's say I want to find all the books that are in the location of Chicago that are based in and have a plot story around Chicago. And you could do that. You could basically reorganize the entire library based on that particular embedding and that search criteria. And so indexing can help you retrieve that smaller portion, because obviously the set of books that are kind of based around Chicago is going to be a much smaller set, and it's going to kind of drop you into that general location and say, okay, here's the set of books you have to look through. So it's going to give you that smaller portion of all available vectors. That's going to help you reduce retrieval time and make this much faster. Okay, so there's lots of different vector options out there. There's all kinds of vector databases. Why would I do this in Neo4j? What's the value here? It's going to let you store structured and unstructured data side by side. So other vector databases, you're going to store mostly unstructured data. You'll have a little bit of metadata you can add sometimes to that, but a lot of heavily unstructured text usually. And the power, though, with graph isn't the connected entities to the vector search. So you'll run the vector similarity search, you'll pull the 20 closest, but then you might take those 20 closest and you'll traverse their relationships and their connections throughout the graph. And then that'll retrieve the extra and relevant context that you can use to help better understand that information. So you have the vector index there on the lower side of the left side of the image there. And that's really powerful for finding similar documents. You have the graph structure where you can do basically pattern matching to kind of drop your cursor, if you will, into a location and kind of sprawl the graph to look for connections of related entities. That's super powerful, but it's when you combine the two and you kind of get this knowledge graph to help you get more accurate results within a relevant context that becomes really powerful. Okay, so I have this existing data. How do I add vectors to that? I know I need a string of numbers here, but that doesn't really help me. How do I get to that? Because I don't have that in my data set currently. So again, let's go back to our data model. We have books, we have authors, we have reviews, we have users. What we're going to do is we're going to create an embedding for the text of reviews. So users will write reviews. They'll write this big, long paragraph of text on whether they love the book and rave about it and all the things they loved, or whether they hated it and all the things they hated, right? And so we're going to take that text, we're going to generate an embedding for it, and we're going to store that back on the review node inside Neo4j. And then what we'll end up doing in the demo portion is we're going to look for review text that has a similar vector to a search phrase. So maybe we want to find a book with a certain theme or something we really like in books. And it's going to go out and look for reviews that have that. And then we'll go out to the graph because the reviews that have that context aren't going to be so much value to us, right? It's like, okay, somebody wrote a review that contained dragons. Cool. But what has that help me? And then we'll go out to the graph and we'll pull those related books and all the information that contains. We could even potentially go out and pull authors and everything that's related to that. So we'll combine the two. All right. So first, how do I get vectors? Back it up a little bit. So we're going to need to generate some vector embeddings. This is going to need to happen externally. So it's a third party, and I think this is the case with pretty much every vector database out there. You're going to need to go out to one of these types of models or many others that exist and generate the embedding. And then you'll bring that embedding back to your database and store it, in our case, as a property on a node. So a couple of examples. I'm going to use OpenAI as kind of the example tonight, but again, lots of other options out there. So on the left-hand side, you have a curl command that's going to basically just call their API and generate an embedding for a specific set of text that you're going to send it, and then it'll return the embedding to you as a result. So you could drop that into a file or pass that along to something else from that curl command. The example on the right-hand side is in Python. And so you can do the same thing, basically call their API, but do this all programmatically through Python. And then as an option with Neo4j, you could use our Python driver to take that embedding and just send it right back into Neo4j and add that to the graph directly from there. Okay, so now how do I use an LLM with graph vector search? That's great. I've got my data set up, but how do I start incorporating LLMs? And so what we're going to use Neo4j to do is called retrieval augmented generation, shortened to RAG. You'll hear that term all over the place. And basically what RAG is it's pulling data from some external data source. Now, this could be a flat file. It could be a web page. It could be a data store, as it often is. But this really is any external data source outside the LLM. So retrieval is going to be data retrieved from that data source, typically a database. Augmenting, you're going to augment the LLM's response with facts you get from that data store. And then the generation piece of it is going to be the LLM's part in that it's going to take that context that was brought from the data store, and it's going to generate a natural language response that it's much nicer to read and more human friendly based on that data. Okay. How much value can RAG actually add? This seems like a lot of work, right? We have to put the data into the database. We have to create vectors from it. We got to make it talk to the LLM and pass that information back and forth. Is there really a whole lot of value? LLMs are pretty cool, right? They're pretty impressive. But what something like a vector store, especially Neo4j, is going to give you, hopefully, is explainable AI. So using RAG and LLM together is, how did the LLM get this answer? Not just, okay, here's the answer. Can we fact check it? Is it sensible? Can we back this up with real data that we have in our knowledge store? So with graphs, you're going to generate some LLM response from the knowledge you're pulling from the database. You can also set some security rules, what's viewable, what's sensitive, what you're not allowed to retrieve, and so on. You can do that all inside the graph. There's lots of rules that Neo4j offers in order to do that. And then you're going to retrieve that extra data connected to those similar entities. So you're going to run the similarity search, but then you're going to be able to kind of crawl the graph and pull more related data as you need to. Okay, let's switch over and do the demo. So I'm going to start I'm going to build a demo application in Spring. So if anybody's familiar with Java and Spring Framework, that's what I'm going to be using tonight. However, all of these concepts and kind of the general architecture of the application itself do translate whether you're using LangChain or something, another framework entirely. Okay. So I'm just going to tweak a couple properties. We're going to call this ACM Chicago. And okay, I've got a couple of dependencies I pulled in here. So I have Spring Web, which is going to let us build a RESTful application. So create REST endpoints for us to call and get data back. And then Spring Data Neo4j. So Spring provides some data libraries that interact with various relational databases or MongoDB or, for instance, Neo4j on the graph side of things that are going to provide some things out of the box that are related and very specific to that data store. So I'm going to incorporate that so I can use some things for Neo4j. I'm going to generate that and drop it into my downloads. And then I'll switch over here and unzip it and open it in IntelliJ. I always like to make sure that it brought in the dependencies we need. So our web dependencies here and Neo4j is here. Now, the other thing I'm going to add is I need to bring in some of the AI dependencies, and these are still in snapshot releases. So they're not general release libraries just yet. So we're going to do Spring AI, OpenAI Spring Boot Starter. And again, I'm going to be operating with OpenAI tonight, but Spring AI actually supports a few different libraries there. So there's some options if you don't do Spring AI, or if you don't do OpenAI, sorry. And the other thing I'm going to add in is our Neo4j vector store. So I have a Neo4j data library that I'm incorporating, but I also need to use Neo4j as a vector store. This is going to let us do the similarity search and a couple other things here. So I'm going to bring that in as well. And you can see that's also a snapshot. So what I need to do is bring in the Maven section for repositories in order to allow it to build the snapshot and milestone releases here. So I just copy pasted that in so you didn't have to watch me struggle through code there. Nobody wants to see me write XML, right? And then we need to put in a few properties. So first up is, let's see, the OpenAI API key. And then we're going to need some Neo4j stuff in order to connect to our Neo4j database. So here we have our username and our password, the URI for the database, and then the actual database. Neo4j supports multi-database as well. Now, typically, you don't want to put all these sensitive properties inside your application. So I've actually set them in my environment, but these would be the properties you would need to set them in an application should you need to. Okay, so let's switch over to our application class here, and we're going to create a couple of beans. Now, for those that may not be familiar with Spring and what is a Spring bean, it's basically a container that's going to house some dependencies that you might need to inject across the application. So I could, drop it into a specific class or, pull it in over here somewhere and utilize those dependencies wherever I need them. So that's what I'm going to do here. The first one I'm going to create is a bean for the Neo4j driver. So I'm going to set that up, and I'm going to return the graph database dot driver, and it's going to need the URI. So I need to pull, because I set these in my environment, I'm going to use the environment variables. So Spring Neo4j URI, and then auth tokens. I'm going to set up my authentication. And we're going to pull in the system.getenv Spring Neo4j authentication username, and then system.getenv and the Spring Neo4j authentication password. Okay, and so there's our bean for the driver so that we can connect to Neo4j. Now we need a bean to connect to OpenAI. So we need an embedding client bean. We're going to call this just embedding client. Super creative, I know. And then we're going to return a new OpenAI embedding client, and we're going to call the OpenAI API. And now we're going to need to pass in our system.getenv, and this is our Spring AI OpenAI API key. And that is a mouthful. There we go. Okay. They didn't ask me when they named all these long properties. Okay. And then the last thing we need is a Neo4j vector store. So we need to be able to call that vector store wherever we need it, right? We're just going to call this vector store. We're going to pass in the driver and the embedding client. And then we're going to return a new Neo4j vector store. We're going to pass in the driver, the embedding client, and then we need to set up our Neo4j config. And instead of the default config, I actually need to specify something that's slightly different. And this is because that Spring AI is looking for an entity type or a node type of document. And because we don't have that in our database, remember we're dealing with books and reviews and users and authors, we actually embedded a property on the review node. So we're actually going to say, hey, look for the label with review. And we're going to build our graph on that, or our vector store on that. Okay. So there's our beans. That looks in pretty good shape. Now we're going to drop over and start creating our application domain. So this is where we start getting into the Spring Data Neo4j stuff. We have our ID of book ID. We have a title. We have an ISBN and then an ISBN 13 as well. Okay, that's in good shape. Now let's go over and create our other entity for review. And we have an ID here. And this is going to be our string ID, string text. And then we're going to have an integer rating. And then we need to create the connection between this entity and our book entity. So our connection between this and our book entity. So we have a written for relationship. And then we have our book entity, and then we're just going to call this reviewed book because somebody's going to write a review for a single book, right? Okay. So with that, now we can create our repository, and this is going to allow us to connect to the database and run queries and pull data from Neo4j. Okay, so we're going to call this review repository, and we're going to extend the Neo4j repository. This is going to give us some Neo4j goodies with the Spring Data Neo4j library. We have a main entity of review, and the ID type is a string. And then we need to write a query. And so we're going to write a little bit of cipher here. And we're going to say, remember, we have reviews. And we're going to pull the related books for those reviews, right? Because we've got an embedding on the review text. We want to pull those related book entities based on those reviews that we're going to get in the similarity search. So we have our review entity. We have our, excuse me, wrong. Write some cipher here, Jen. Written for relationship. And then we have our book entity on the other side. Now, so we're going to be passing in our IDs from the reviews that we're going to get from our similarity search. Because remember, we're going to run a similarity search. It's going to pull back the reviews that are most similar to that search phrase. And then we're going to need to pass in those review IDs in order to pull back the related books. So we're going to say where r.id is in a set of review IDs. And I'll show you how this is set up in just a second. It'll make more sense. And then we're going to return our review. And basically what we're going to do is we're just going to collect the related entities into a list so that we ensure that we have a single record for a review that's based around the books that it's related to. Okay. And then we're going to have an iterable of reviews coming back. And we're going to call this find books. I know that seems a little confusing, but we know we're using this to retrieve the book entities, right? And then we're going to pass in a list of strings, and this is going to be our review IDs. Okay, let's go back over to our main project here, and we're going to set up our review controller, and this is where it'll start making a little bit more sense. Okay, so we need to annotate this as a REST controller. We need to also add an annotation for the endpoint, the initial endpoint. We're just going to leave this at // for now. And then we need to inject a couple of things. So the first thing we need to inject is our OpenAI chat client. So this is going to allow us to interact with OpenAI in a chat-like manner. And yes, it's mad at me. It wants me to inject it into a constructor. We'll get there in just a second. The next thing we need is our embedding client, right? No, we've already got our client. Never mind. We need to inject our review repository here. We're going to call this repo. So that's going to allow us to execute the method, the query that we just set up in the review repository. And then we also need our Neo4j vector store here. So we're just going to call this vector store. And yes, okay, we're going to say add constructor parameters. We want to create all three into a constructor, and now it's happy. Okay. So let's actually dig in and we'll create our endpoint now. So we're going to call this /rag, and we're going to return a string. We're going to say get generated response with context, because we are actually hitting the graph, right? We're going to send a request parameter across. And we're going to pass in string search phrase. So we want somebody to search a particular thing they like in a book, and then we're going to retrieve the similar things there. Okay. So for now, I'm just going to say return text just to kind of keep it happy. We'll fill that value in here in just a second. Okay. The first thing we want to do is we need a list of documents. And we want these AI documents because, again, this is what Spring AI is looking for. It's looking for an entity type of document. Now, what we'll end up doing, because we're using Neo4j Vector Store, that library actually lets you convert the whatever entity you're using inside the graph to the document. So it'll take care of that mapping for us. And we're just going to say results, call this results, and then we're going to access our vector store, run the similarity search method there. We're going to pass in a search request. And the query we're going to use is we're going to pass in the search phrase. And then we want to retrieve the top, let's say 10 results. I figure if you have 10 results, 10 reviews, that should give you somewhere around 5 to 10 books that you can give as a recommendation, right? Which sounds like a pretty good number to me. Okay. The next thing we want to do is, not an iterator, an iterable of reviews. And we're going to call this book list because, again, even though we're retrieving reviews, we really are interested in the books that are coming back related to that, right? So this is where we're going to pass in the results. We're going to call our repository.findBooks method that we set up in our review repository with that nice Cypher query. Then we're going to pass in the results that we get. But remember, the results that are coming back are a list of documents. And we maybe just want to send the IDs over because we don't need the whole document being sent over. So we're going to stream that list of documents. We're going to map each of the document IDs that we get out of that. And we're going to map that into a list. So we're going to take each one of those IDs from each document. We're going to collect that into a list and send that over to our find books query that's going to run. Okay. Make that happy. Okay. So now we have our similarity search. We've brought the similar vectors back as a list of documents. Then we're going to take that list of documents. We're going to go out to Neo4j and we're going to pull the related context of the related entities to that and then retrieve that back. Now, the only thing left we need to do here is create a prompt to send over to the LLM. So we can pass in that context and the thing that somebody is searching for and send that to the LLM to help us format a nice response. So we're going to create a new prompt template. And then need a couple of things. And this is the only other piece that I'm going to copy paste because nobody wants to see me write this big long text prompt, right? So basically you're providing book recommendations for books with reviews similar to the searched phrase. And it's saying, if you're unsure, list the book title. It's going to pass in the context that we're going to get from this book list, and then the search phrase that somebody is querying, right? So we actually need to map those values here. So we're going to do a map.of. I'm going to go ahead and put the semicolon on the end there. So we have context variable here, and we're going to use the book list value to fill that, and then the search phrase one here we're going to pass in the search phrase value, and that's going to populate that. Now, the other thing I like to do here is so that we can see what is actually coming back from the database and what's getting sent over to the LLM. I like to throw in this little bit of a system.out.println so that we can see what all information is getting sent. And we can actually back up the LLM's answer with some details here. So we're going to take our template and we're just going to render that. Okay, now we need to fill in this because we obviously can't just return text. It's not super valuable. So here we're going to do our client.call again. So this is going to reach out to the OpenAI chat client and use this template to create a message. So we're going to do that here. Template.create. That's going to create our message. Now, the object that's going to come back for that is going to have a lot of stuff in it. So we're expecting a single result, right? Because the LLM is going to generate one response. And then we need to pull the output from that and then the content value from that object. Okay. So that should give us a string in return. And if I have played my cards correctly, this will be one happy little demo. We'll see. ACM Chicago. And let's do a Maven W Spring Boot : run. I hope I've typed that correctly. There we go. I had to move a little pop-up message that was sitting up there. Okay, so if this is all happy, which so far is looking good. Okay, I think we're in good shape. So I'll create a new tab here. And then we can hit our endpoint and see what reviews are coming back. So HTTP 8080 is kind of the natural port that Spring Boot uses for endpoints. And then we have our /rag, and then we need to pass in a search phrase. And we're going to say, we want to look for books with, let's say, fairy tale endings. And the %20 is the character for space. So we're going to look for something that has fairy tale endings in it. Let's see what it comes back with. Okay, so I Still Dream About You, and then Big Girls Do It Pregnant. And I'm unsure about other recommendations. So remember, let's go see what it sent to the LLM and see if the data looks halfway decent here. So here we have a review. The text is an amusing fairy tale. So that seems pretty logical. The title, I Still Dream About You. That was one of the results it returned. Here's a review, a great happy ever after tale. That looks pretty good. Oh, that one actually didn't come back. So here again, you've got a little bit of LLM injecting its own logic in there. But okay, there's some other things in here as well. I know that, oh, here's the other one it gave. This one down here. So where's the review? Beautiful, happy ending. Okay, so not specifically fairy tale, but it is one of the results that came back from the graph database as well. So, okay, that looks pretty reasonable at least. And I could probably do a little bit more prompt engineering on this to make it a little bit stricter and such. But let's try another example here. Let's see what we get for Jedi. I'm kind of a Star Wars nerd. Let's see what it finds. I've read a lot of the Star Wars books, actually. So, okay. So it pulls back actually several. Normally it's a little bit more specific about this. Okay, so we have Labyrinth of Evil, Star Wars, the Dark Lord trilogy, and then it's got some other here's a duplicate title actually. That's interesting that it didn't weed that out. So if we go look at the context that's being sent, we have our text here, which again, nothing about Jedi, but somehow it's getting pulled in the similarity search. And then here's the title of the book that's actually getting sent. Okay, not super logical. So the LLM didn't return that one. It didn't see it as being close enough, which is good that it weeded that out, I guess. And then we have this text, which kind of looks like gibberish. But I mean, it doesn't really look like Jedi, but I can kind of see where it got that. But you can see that the title is in a foreign language. Okay, so the LLM weeded that one out too. But the one down here, you'll see some review text here. Love finding out the events leading up to Revenge of the Jedi. So there it actually lists Jedi specifically. And this one is the Labyrinth of Evil, Star Wars, Dark Lord trilogy, which it did return. Actually, it returned it twice. Normally it doesn't do that. So here we go, LLM making, kind of having its own little brain on this one. Okay, so that one's interesting. And probably if we ran it again, it would give us something slightly different, which I may try in a second if I've got time. But okay, let's search for dragons because I like a good fantasy book as well. Let's see what it gets back here. So we have Throne of Jade, we have Draconomicon, and we have The Dragon Claims His Treasure. And it does say it's a little bit unsure about this last one. So let's see what the graph brought back for us. Okay, we have this first review. It says, ooh, dragons, which, hey, that matches our search criteria, right? And this is the Throne of Jade. So that's the one it returned. So that looks pretty good. Very good description of dragons for this review. And this book is the Draconomicon, the Book of Dragons. So that looks good. If you like dragons, read this book. That's again, Throne of Jade. So you'll notice that now we have multiple reviews of the same book coming back. Now that's interesting. You could weed this out and say only return unique books that are coming for these reviews, but I actually kind of like it surfacing multiple reviews that have that same search phrase in it, because that kind of brings those to the top of the stack, right? If you have multiple reviews saying, hey, this is about dragons, this is about dragons, this is about dragons, it's a good indication that it's about dragons, right? And that's what we're looking for. So that's a good one. So there's another Throne of Jade. Let's see, Throne of Jade. So that one's coming up quite a bit. We have this one. It's also Throne of Jade. Where's the one? It should be, we should have, oh, the dragon claims its treasure. There it is. So it talks about, finds an alien dragon shifter. So it does mention dragon there as well. And that's the dragon claims his treasure. So that one's looking good as well. So it brings back those three. I don't see any others. All the others are just kind of multiples of this Throne of Jade one. So that looks really good. It's a nice list. And it even says it's kind of unsure about this one because it talks, I think, a little bit about alien dragon shifter. So it may not be quite as much about dragons potentially there. So, okay. But it's doing a pretty reasonable job there. It's pulling the context from stuff that we know. If we asked these questions of just the LLM itself, it would probably be very generic and it might not come up with valid results here. This, we can fact check it with the data and the knowledge base that we have in Neo4j to say, yes, these are the titles that it's bringing back. And then the LLM, and in this case, because of my prompt engineering, is kind of giving us a logical list of what it thinks the best results from that context are, right? Okay, so with that, then we can switch back to our presentation and wrap up with a few resources here. So all of the code that I built for today, and I think actually a little bit more, there's an endpoint that just calls the LLM and sends questions to it, so you can test that out individually without doing the vector stuff. And that is available in that first link for the GitHub repository. So everything we wrote today, plus a little extra, is there. And then if you're looking more information on how to use LLMs and Neo4j together, we have some really nice online self-paced and free learning courses on Graph Academy. So under our LLM section, I know there's 2 out there for sure. Both are very good, but we've got some more that are upcoming, hopefully to be released soon. And then documentation for Spring AI, if you want to know more about Spring AI in general or how it works with vector DBs like Neo4j, I've got that link here in the third one. And then lastly, if you're interested in more about the embedding side of things, how to generate those embeddings, I've got the OpenAI documentation linked there as well. As always, feel free to reach out. My contact information is there in the lower left, and I'll definitely stay on and answer some questions because it looks like we are just in time. So thank you very much.
All right. Thank you very much, Jennifer, for that wonderful presentation. So we have some questions. And Mark, can you also, we also have a poll too as well. So maybe if you can start the poll while there we go. So you can answer those questions while we go ahead and go with Q&A.
All right, our first question is, I'm going to be using Neo4j again after a number of years for 2 upcoming projects. I work in Ruby and would like to deploy to Heroku. Do you know how easy it is to use a Neo4j software as a service in that kind of environment?
So I'm not super deep in the Ruby space. I've used a little bit of it before, but not super experienced there. But I know we do have a Ruby driver. And then deploying to Heroku, I know we've got several projects that deploy to Heroku, and that's one very common one we deploy to. So I think that does pretty reasonably. I can try to find a better answer than that. Again, not an expert, but I can find somebody who is to give more specifics on that. But I know we do have support for Ruby, and we also use Heroku quite regularly. So I don't imagine that would be too much of a problem.
Okay, apart from RAG, what's your take on using a knowledge graph to fine-tune a foundation model?
So you can fine tune a model that typically ends up being really expensive. So what most businesses and applications end up doing is they'll use the data store as their knowledge graph to supplement the existing models. You can absolutely inject, your own knowledge into it and regenerate the large language model itself. But again, you're having to run that on lots of servers, and you're spending a lot of kind of RAM and CPU and probably money in that case to help fine tune those models very specifically. So that's not going to be kind of the general broad use case. What most people are going to end up doing is something like RAG. But you can absolutely use knowledge from a particular data store in order to create your own fine-tuned model. It's just not overly common, I would say.
How is the author of a book encoded in a vector in a way that nearest or similar vectors can be found?
So we actually have not encoded authors at all. That is just stored in the database as a connected entity. So what we've created embedding for is the review text. So if you remember the data model we had books and we had related authors, we had related reviews and related users. And so book and review, we took the review text that somebody had written and we embedded that onto the review node. And then when we did the similarity search, it retrieved review entities, but it didn't retrieve anything else around it. So that's why we went back to the graph and said, okay, I have this list of similar reviews. Now I want to retrieve the books they were written for. And so that's when you go out to the graph. We didn't embed or encode anything else inside the graph, just the review text itself.
Okay, here's a comment about the demo. This doesn't appear to prevent hallucinations, but it does at least provide useful context as to why the LLM got confused. For example, your search for Jedi returned a book where the review reference needs more Jude.
Yeah, and this is partially because I didn't have a large data set that had Jedi. And again, it's going to pull the most similar vectors. So the top 10 in this instance. So even if they're very far distantly related, and that's where you could set something in the similarity search for a temperature threshold. So say, okay, if it's not within a 0.5 related, then like a 5% relation, then don't even return it. So I could be a little bit more selective about the similarity search there. But I didn't this round. I just pulled the top 10 closest that I had in my data store. And I could absolutely clean some data up and things like that too, that would improve those results even further. So again, you have to have good data quality inside your vector store. And then you have to be able to kind of fine tune that a little bit inside to make the LLM kind of work with you a bit on that. So yes, it's not going to completely eliminate hallucinations, but it'll do way, way better. I've seen some numbers out there that say, okay, using some kind of data store in the back is going to improve anywhere between like 10 and 20% of the LLM responses there. So just to be able to kind of set that knowledge basis for the LLM. And then again, a little bit more prompt engineering would probably help retrieve very specific results and not let it do any sort of hallucination or external stuff at all.
Okay, and two more questions. So person was curious about whether Neo4j's vector store has the ability to load very specific data as the metadata. For example, could it contain the following: book name, chapter title, page number?
Yes. Yeah, so we've done some examples where we've pulled like financial documents, and we'll chunk up, because financial documents, of course, are pages and pages and pages long. And so you can chunk up that text and kind of create these individual smaller segments, and you can embed each one of those and then do similarity searches on that. So if I had, even just kind of book descriptions, or if I had entire book texts, I could absolutely do that and look for specific paragraphs or specific chapters or segments of books that contain certain things or themes that I'm looking for. So yes, you can do that. There's lots of examples out there, especially when you look at like financial documents or a lot of times academic articles, they'll do that with as well. I know there's examples out there for those specifically.
Okay, and for our last question, what is it that is vectorized, and how do you convert that item into a numerical vector so that it can be compared to others so as to determine similarity?
Yes. So what is getting vectorized kind of depends on the data. Like some people will vectorize video format or text or audio. And ChatGPT is vectorized text, right? And that's typically what you will see. You'll take some unstructured document of some sort. So people have this knowledge base of random documents, maybe lessons learned documents or financial documents from like for instance SEC filings in the US. Or you'll have just a random knowledge base of documents. It's all unstructured text, and they'll take that text, they'll possibly chunk it up into smaller segments so that you can create embeddings from it, and then they'll embed that section of text or those sections of text. And then from those embeddings, you can then run the similarity searches. So in our case, we just took the review text, but you could do any segment of text, and you can even do like audio or images or video or something else entirely. There's tons of stuff new coming out. You can create vectorized embeddings of stuff. But again, you're going to need to go out to a third party. So things like OpenAI, Vertex from Google is going to do it. We have our graph data science library that will create vectors from data, and some other resources as well. There's lots of third parties out there that will create embeddings from a data thing, a data item, if you will. In our case, it's just a chunk of text. And that's typically what you'll see. You'll take unstructured data, text, go out to this third party to generate the embedding, that string of numbers from that. And the third party will handle all of that. And then you'll store that embedding somehow in your data store. So I hope that answers your question. If not, feel free to follow up with one or ping me later too.
Okay, and sneak in one more last question. Are there good SaaS, software as a service providers for Neo4j?
Yes. So all of the I assume you're talking like hosted. I like to host Neo4j. If that's the case, all of the major cloud providers will host Neo4j. So Google, Google Cloud, and AWS, and Azure as well. So you can host them all there. And then, of course, things like what was the one that was just mentioned, actually? You can run from there as well. So you could run Neo4j, host it anywhere in the cloud.
All right, great. Thank you very much, Jennifer, for that. Our next presentation is going to be a live presentation. So it's going to be in person, and it's going to be about a month from today, March the 20th. It's going to be our first in-person for this year. And we actually have a ACM distinguished speaker. So ACM has a list of distinguished speakers that can be invited to ACM meetups. And so we've been really privileged to be able to request Sheldon. And Sheldon, actually, he's a professor at University of Illinois, Urbana-Champaign. So he's actually going to personally be traveling to come to Chicago to the Loyola University Lakeshore campus to give a talk on analytical models for generating NCAA men's basketball tournament bracket pools, injecting computation into March Madness, because it is March Madness, right? During March for the NCAA basketball tournament. And yes, so of course, like what Mark said, we're always looking for more speakers. So this is a wonderful opportunity to talk about, your work or stuff to a technical audience. So if you're if you're one of the attendees here this evening, and you want to, talk about some stuff that you're doing at your company or some development stuff or research, we very, very much welcome that. So please reach out to us at vice chair chair@chicagoacm.org or chair@chicagoacm.org. And then there were some, comments on the chat regarding about, recordings. So all our recordings of our previous meetups, as well as this one that we will process afterwards. If you go to our YouTube video channel, so which is https://bit.ly/ACM CHI video, which I also posted in the chat. If you go ahead and go to that link and you subscribe to our YouTube video channel, then that is the best way to determine when you will get a notification for our new upcoming videos that are recorded. So rather than you having to, email us and say, oh, is a recording available, just subscribe to that YouTube video channel. And then when the new one happens to be uploaded, you will be able to receive that. And then, of course, a copy of Jennifer's slides will be made available, and we'll post that on our website at chicagoacm.org when it's ready. And then, of course, what we do here, this is not our day job. We do this, as volunteers. So, it's the volunteers that, make what we do here successful. And so, we have a call for, volunteers to help us with this in ACM Chicago. So if you have, any particular skills in writing, in planning, or doing videography, we would be would be really happy to get someone who, is well-versed in doing some editing of video, so we can provide some professional, kind of recordings that we can be able to, share with other people. Also, as well, if you know of any other speakers and topics that you would want to see, please let us know too as well. And also by joining, as a volunteer, you really get to understand and you get to meet with other particular people and kind of spread the interest in computing. So, and bring back to the community. All right. So, okay. So with that, we're pretty much done for this evening. So thank you everyone for joining. And thank you for submitting the poll. So wish everyone have a very good evening. And if you need to have a PDA certificate, you can email me at chair@chicagoacm.org. And with that, thank you again, Jennifer, for presenting this evening on Neo4j. And if you have any further questions, Jennifer has her email that you saw from the PowerPoint, and we will share the slides. So if you have any questions that were not addressed this evening, you can go ahead and email her directly. All right, so thank you everyone for joining. Have a great evening, and hope to see you at our next one on March 20th. All right, thanks everyone.
Bye, thank you.
Bye.